This is pre-calculus section 10.5 on parametric equations. And most of the equations we've looked at deal with two variables, and generally that's going to be x and y. However, we're going to throw in a third variable of t, and we can think of that variable t representing the time. So let's go ahead and get an idea of what a parametric might look like. We have two different equations. There's an x value and there's a y value, and they both are a function of t. So if I want to know where is this graph located when time equals 0 at the very beginning, I could plug 0 in for t. So if I plug it in for the x equation, plug it into the y equation, I get a point at 1, 0. So at 0 seconds, it's at 1, 0. If I plug in 1, then evaluate for both of those values. We get 3 for x and 5 for y. And I can keep going. If I plug it in an x value or a t value of 2, I get 5 and 10. So then this gives me an idea of what the equation is going to look like. I have a point at 1, 0, point at 3, 5, and a point at 5, 10. And I can see that in this case, this graph is going to be a line. Let's take a look at this equation on the graphing calculator. And if you hit the mode button and then scroll down to the fourth line, we've always had it in function form so far. If you scroll one to the right, that would be parametric. So highlight that. And now if you hit the y equals button, it's not the normal y equals. You have x1 of t and y1 of t. And we're just going to enter those in exactly like we have in this problem. So x1 of t equals 2t plus 1. y1 of t equals 5t. And to get a good window of this one, let's set the t min at 0. T max, let's go to 20s. In other words, we're going from 0 to 20 seconds. T step, we'll put really small at 0.01, so we're seeing every 1/100th of a second. And because I've already graphed this one, I'll tell you that the x and y values will go from 0 to 50 for x. So our x min is 0, our x max is 50. The x scale we don't really care about. For y min, let's go to 0 also, and y max will go for 80. And then if you hit the graph button, you should see the same thing that we were just talking about. And one thing we did with this on the window is we have the t step at 0.01. Go ahead and hit window again, change your t step to 0.1, and then hit graph, and you'll see that it goes faster, in fact 10 times faster. If you hit window again, change the t step to 1, and then hit graph, it goes really fast. So we can change how fast it's going by the t step. Now if you're getting into a cycle where it's going really slow, and it's just not graphing it very quickly, it seems like it's taking forever, then if you hit second on, which would normally turn the whole calculator off, it will actually freeze that, and then you can do whatever you want with the calculator so that you're not stuck in a mode that's going to take forever. All right, so let's do some conversion here. We have this equation that's just in the normal function form, and we want to convert it to parametric form. And generally, the easiest way to do that is to just let x be equal to t. We're always going to do that because that's the simplest way to make this work. We're going to say, okay, if x equals t, and then we would plug that back in where we see that x, because x and t are now the same thing, and we get y equals 3t plus 5. So then this parametric graph is equivalent to the original. It just has a time value attached to it. We'll do a similar thing for this next one. We'll let x equal t, and now if you plug t in over here, we get that y equals t squared plus 3. So when the graph is being graphed, when this parametric is being graphed, it's graphing all the x values, it's graphing all the y values, plotting all those points to eventually get the curve of the graph. Okay, next we're going to go in the opposite direction. We're going to convert from parametric into rectangular. And as I look at this one, both of these equations are linear. There's no squares or anything in them, which to me says I'm just going to treat it like it's a line. And I'll make a quick chart here. T, x, and y, and I could pick any values for t that I wanted to. I might as well make it as simple as possible. If t equals 0, plug it in for both of those equations. That means x equals 0 and y equals -4. And then if we have t equal to 1, we get an x value of 3, plug it in for the other one, and we get a y value of -2. And what that does for us is it gives us 2 points that are on this parametric. We could have chosen any values of t that we wanted to. Again, I chose the ones that I thought were the simplest. So now, and again, because I know it's a line because of what these equations look like, I can calculate the slope. Let's see, that's going to be -4 minus -2 over 0 minus 3. -2 over -3, which is 2/3. Now for the y-intercept, I see I have a point at 0, -4, so our b value is -4. The equation is y equals 2/3 x minus 4. So if you were to graph this equation and compare it with graphing this one as it still is in the parametric form, you would get the exact same graph. Okay, our next one. Now this one is not linear. The x value is linear, but since the y value isn't, we're going to do something a little bit different. In fact, we're going to solve this first equation for t. So if I do that, I would get that t is equal to x minus 2. We're going to take that fact and plug it in for t in the other equation. So now the second equation that started off with y and t becomes y equals x minus 2 squared plus 3, and we have our graph. So the original graph in parametric form looked like this, and now in rectangular form, the standard form or the normal form, if you want to think about it that way, is this. Okay, here's our next example. Again, this is one that I see looks a little bit different. It's not just linear. So I'll take the x value and solve it for t. I could solve the y value for t, although that's not really preferred. I want to eventually have an equation in rectangular form as a function that solves for y. And it's also easier to solve this for x. T is equal to x divided by 2. We're dividing both sides by 2, and I will plug that in for t. So then y equals 4 over x over 2 minus 2. Now I don't want to leave this as a fraction within a fraction, so we're going to multiply the whole numerator and the whole denominator by 2, which would give us y equals 8 over x minus 4. So now here we have our equation in rectangular form. Next example. This one obviously looks more confusing than the other ones because we don't just have it linear. It's not even just squared. We have trig functions brought into it. So here's my strategy this time. Theta, first of all, theta is like t. Theta is like our time variable. It's our third variable. If I was going to try to solve this one for theta, I'd be taking a cosine inverse, and I don't really want to get into that. So what I'm going to do instead is solve it for cosine of theta. X over 5 is equal to cosine of theta. Seems like maybe it's a bit of a dead end at that point. However, we're going to do the same kind of thing for y. Y over 4 is equal to the sine of theta. Now, if you think back to our study in trigonometry, there was a Pythagorean identity that related cosine and sine together. One thing we could do is we could take sine divided by cosine and get it in terms of tangent. That's not going to be preferred here because then we'd have multiple fractions, which makes it more confusing. Instead, the other way we can combine cosine and sine together is with remembering that cosine squared plus sine squared is equal to 1. So if we take this blue equation that's in terms of x and square the left, which means we're squaring the numerator and the denominator. And for the red one, the one in terms of y, we'll square both sides also. So y squared over 16 equals sine squared. And then bringing those together, since this is equal to cosine squared and this is equal to sine squared, then gray plus gray is equal to cosine squared plus sine squared. And again, cosine squared plus sine squared equals 1. So our final answer here is going to be x squared over 25 plus y squared over 16 is equal to 1. So this equation that we were dealing with from the very beginning in parametric form is really this. So the original equation and this new one both are ellipses. They're centered at 0, 0. We have vertices at 5, 0, negative 5, 0, co-vertices at 0, 4, 0, negative 4. There's a lot of things we can do with it in this form. All right, next example. Same type of problem, just requires a little bit more work. I'm going to solve the first equation for cosine. First of all, we would subtract 2 from both sides, then divide by 3. That would make this equal to the cosine of theta. And for our second equation, we're going to add 4 to both sides, divide by 6, and then that's equal to the sine of theta. I'm doing it like this because, again, I remember that cosine squared plus sine squared equals 1. So if we square the red equation, we would get the quantity x minus 2 squared over 9 equals cosine squared. And then for the green one, we'd have the quantity y plus 4 squared over 36 is equal to sine squared of theta. Since cosine squared plus sine squared equals 1, we're going to say that x minus 2 squared over 9 plus y plus 4 squared over 36 is equal to 1. So again, we have another ellipse. This time it's centered at 2 comma negative 4, and from that we can get our vertices and covertices. Next up, we're going to look at some graphs on the graphing calculator. So if you go into your graphing calculator and enter in x sub 1 equals sine of theta, or might have you put it in as sine of t, and that's fine. Y equals 3 times the cosine of 3 theta. And in order for this to work, I want your window to have x values from negative 5 to 5, put brackets because we're going to include that, the y values from negative 5 to 5. We'll also set the t values from 0 to 2 pi. And the reason why I'm doing that is because this is trig functions, sine of theta and cosine of theta. They both have a period of 2 pi. So this should give us everything in the graph. Have the t step equal to 0.1, or maybe even something smaller, 0.05 maybe, just so you can see as it's going. If you have that number be too big, it won't be as precise. It'll jump around a lot more and it won't graph it. When this one is done, it looks kind of like something kind of like that, kind of like a face with like really big ears on the side, like a Martian face maybe. Next one, we're dealing with trig functions again. The other thing I forgot to mention in this previous problem was we need to make sure that we are in radian mode. Maybe you gathered that because we were going from 0 to 2 pi. If we went from 0 to 360, then we could have the mode in degrees. But generally, when we're working with trig functions and we're graphing, we want those to be in radian mode. So make sure you're in radian mode for that, and that's what the graph should look like. For the next example, we'll have the windows be pretty much the same thing. The x values, the y values, the t values, the t step, and we want to make sure that we're in radian mode. And the graph for this one looks something kind of like this. And you're not going to be expected to look at the equations and predict what's going to happen. It's just a matter of knowing that we can get some strange graphs out there. And the interesting thing about all these graphs, or any of these graphs we're looking at, not necessarily all of them, but there's the potential to get something that doesn't pass the vertical line test, so it's not a function. When we were in the function mode rather than the parametric mode, it could only graph functions. But if we put it into the parametric mode, we can see that it fails the vertical line test at a lot of locations. So this gives us a way to graph those things, such as the ellipse or the circle. Now for these last two examples, we're looking at changing into parametric form. And there's more than one correct answer for this first one, just depending on what time we were talking about, but this is going to be generally the easiest way to come up with one of the potential answers. We're going to say xy is equal to 2 comma 5 plus t times negative 1 comma 14. Actually, that's not correct. 2 comma 5 plus t times, and the reason why it's not just negative 1 comma 14 is because in this one we want the change. If I call this point A and if I call this point B, we want to look and see what is the change actually doing here. Going from an x value of 2 to an x value of negative 1, the x value changed by negative 3, and the y value went from 5 to a y value of 14. I see that y value increased by 9. So here is a start to this one. Again, it's just a general x comma y equals starting at this point, although I could have started at this one and then gone to the other one, but starting here and going to the other one. Now we'll write it in parametric. We'll take the x values, so x equals 2 plus negative 3t, or 2 minus 3t, and then for the y values, we'll take the second term in all of these. So y is equal to 5 plus 9t. So now we have it in parametric form. It's going to go through both of those 2 points. And here is our last one. If this is the center and this is the radius, that means that x minus 5 squared plus y minus 2 squared is equal to 16. So there's our circle in standard form. And then we're going to break it up into parts. Let's take the x part of this one first. We're going to say that this x minus 5 squared is equal to 16 cosine squared of theta. And we're also going to say that y minus 2 squared equals 16 sine squared of theta. Okay, so how did I come up with that? So look back at our problem. What I could do here is multiply this by cosine squared plus sine squared, or sine squared plus cosine squared. But I'm going to do the cosine squared first because, again, if you think back to trig, x and cosine are always related to each other, y and sine are related to each other. Since I'm multiplying the right side by this, I'm really multiplying it by 1. Multiplying by 1 doesn't change anything. And if we look at the parts, we'd have this equal to 16 cosine squared of theta, and we'd have the y value equal to 16 times sine squared of theta. So that's how we're coming up with those two equations. For the first one, take the square root of both sides, and I'm just going to deal with the positive roots here. So x minus 5 equals 4 cosine of theta, and I'm trying to solve this one for x, so then I'm going to add 5 to both sides. So x equals 5 plus 4 times the cosine of theta. So my x value is good in parametric form. And then for the y1, I'm going to take the square root of both sides also. So y minus 2 equals 4 times the sine of theta. Add 2 to both sides. Y equals 2 plus 4 times the sine of theta. If I want to verify this on the graphing calculator, I could get an idea of what the window needs to be by graphing the original. The center is at 5, 2 with a radius of 4. I know the graph should look like this. So on my window, if I'm going to graph it once I have it in parametric form, I want my x value to be maybe somewhere from 0 to 10. The y values from about -6 to +8. Because this is a trig one, I want t to go from 0 to 2 pi as long as I'm in radian mode. And then the t step is significant. Make that something small like 0.1. And when you're done, you should get a circle. Now, depending on the window we're looking at, it might skew it a little bit. It might make it look more like an ellipse if it's too far to the horizontal or too much vertical. But it'll give us an idea if we have an accurate answer here.